Hello. Welcome to the last week of the last week. All right, so let's just start. But before I start, there is a question or concern. I sent you an email yesterday or the day before. Any questions you want to add? We have yes, you can have a full machine and you can have everything you want on one email, yes, one page, letter size, back and forth. You can have anything that you want. Anything else? If you have any questions or concerns, you can always send them here. And you saw I set up new office hours, which you are welcome to. So let's start with our previous discussion. Just as a quick recap, we discussed the vibration of a string, which we ended up to a 1D wave equation. Then we started the vibration of a beam, and we ended up with a mode shape, which looks like that. As a particular example, we solved for a cantilever beam. Right. Just something to clarify, because I got a few questions, just to make sure that you understand. Because the math, I'm sure you can go and figure it out. Just the concept to exactly understand what's happening. So imagine that you have this cantilever beam that I draw. Right? So this cantilever beam, we can excite it the way that we want. Let's say I weld this cantilever beam on the back of my car or on an airplane. Or imagine this cantilever beam is part of maybe an airplane or a helicopter or a car. One part, something. Or maybe something that you hook to yourself and you're walking. Right? So as a result of this external excitation, let's say when you attach it to a car and car is on a road, you are exciting different frequency of these cantilever beam. And this cantilever beam has infinite number of natural frequencies. Depends on which frequency you are exciting or you are close to that natural frequency, that mode can be dominant. Let's say if I excite this cantilever beam only with frequency of ω1. Imagine that I'm holding this cantilever beam, all right, on the support, and I'm moving it ups and down. Nothing special. I'm just moving it ups and down with a frequency of ω1, which is a number, right? Frequency of ω1. If I have the modulus of elasticity, I and the rest, I can find that natural frequency. So if I move this back or this support, let's say with a frequency, the amplitude doesn't matter, with the frequency which is close to ω1, then my beam is going to get a shape like that one. So that's going to be the dominant shape. If I excite it with a natural frequency of ω2, then my beam is going to get a shape which is this one, right? So, but if I excite it with a bunch of frequencies, as I said, let's say you have this cantilever beam, you attach it to a car, you weld it to a back of a car, and the car is on a road. So you know there is going to be a lot of frequencies. So this beam is going to get a weird shape, this green one, all right? And this green one now comes from contribution of many, many modes. Each of these modes can have different contributions. Some of them might be tiny, tiny, very small. Some of them may be close to zero, but some of them might be the dominant one. Depends on which frequency we are close to, all right? So that's the whole idea. I have a cantilever beam, I vibrate it with different frequency, so I get this green shape. This green shape comes from combination of all modes, which there are infinite numbers of them. But typically, as I said, after mode 6, 7, the frequency is so high that we say their contribution when we calculate, when we do the math, is very, very small, unless we are caring about the very, very high frequency vibrations. All right, so that's something to clear up. And I guess it was you, Gibson, right? Yeah. Ask, how can I excite all the frequency for this beam? Yeah, it was you sitting over there. So for the test that people do, all right, so let's say I have a table or a cantilever beam, and I like to know what are its natural frequency. Of course, I can do all these calculations, but let's say I want to make sure and I want to check. Or maybe the shape is too complicated to do the calculation, and I like to do it experimentally. What people does, they put an accelerometer somewhere, which is out of the scope of this course, but you go to the grad school, you will do that. I have the equipment if somebody is interested later after the semester likes to do the test. They put an accelerometer there, and they try to, or several accelerometers, depends on how accurate you want. Let's say you put several accelerometers, so you get this green shape, all right? So now the question is, how can I excite a bunch of frequencies? One way is that you have a shaker, you set it up to frequency of 1 hertz, then 2 hertz, then 3 hertz, and go all the way to 10,000 hertz, with the hope that maybe one of these excite one of these modes, all right? So, but in reality, it's not possible. So what people do, they use a hammer. And there is a particular hammer, which is called modal hammer. It's more like the doctors, they hit on your knees. So engineers have this hammer. I have one of these hammer, small hammer, which you just bang on this cantilever beam. So then you may say, well, this is just an impulse. But when you do an FFT of an impulse, it is, let's say, if I have in a time domain, and as I said, this is out of the scope of this course, and you don't want to go over that. So this is time, and this is the amplitude, which is force here. Now I'm using a hammer. When I apply, let's say I bang on this cantilever beam. So imagine there is nothing, and all of a sudden there is an impulse load, and then there is nothing. Let's say I apply load for half a second, or maybe shorter than that. So this looks like a half sine. Do an FFT of these things, so you can try it on your own with the code that I put on Canvas for doing FFT. If you convert that time domain to the frequency domain, and this is an amplitude, so you will be surprised that the frequency, in frequency domain, it looks like that. And over here, it is like maybe 100,000 hertz. So it means you just one impulse, you excited the frequency up to 100,000 hertz. Of course, this 100,000 hertz is just an arbitrary number. It can be 10,000 or something else. Depends on how fast we can apply this impulse. And in fact, this is a skill, like the people who do modal analysis with their hammer. If you, let's say, hit the cantilever beam or the object very fast or very short, you get different results. So it depends on what you want, right? So that's the whole story for experimental test. But again, what you need to know in terms of, let's say, for this course, is you have a beam, it has infinite number of natural frequencies and mode shapes. Those all depend on the boundary conditions. What is this end? What is the other end? And you saw based on these boundary conditions, we got to these yx. And if I change these boundary conditions, the shape will be different. Right? So, and sum of all these mode shapes, I'll get to the actual result. So it was a quick simulation that we did last lecture, the cantilever beam, which I showed you. And as you can see, I have mode 1, 2, and so forth. It is for a material which is steel. Here is the cross section. And the cross section, by the way, can be anything. It can be a circle. It can be, you're not limited to a cross section of like a square shape or rectangular shape. Here is the length. I have the material, and here are the first 4 natural frequencies. As you can see, as I go higher and higher, the natural frequencies increase. And something else that we discussed is this point. As you can see, they have 0 displacement, which we refer to them as nodal points. Points that their displacement in that particular mode is 0. So let's say I'm doing a test and I'm putting my accelerometer for the test over here. And I excite this beam, and it happened the excitation to be omega 3. Then I see this accelerometer shows me the value of an accelerometer. It shows me the value of 0. So I think that maybe the beam hasn't been excited at this frequency. So, but this is wrong. It happened that let's say accidentally, I put the accelerometer in a nodal point, and that's misleading. So I'm reading 0. That's why when people do tests, these modal tests, they put several accelerometers at different points to make sure that their accelerometer is not at the nodal point. Just some extra things to know. It has, although it's just a simple cantilever beam, but it has many, many applications. One is these blades, which simple blade can have 4 blades. On each side, we can model it as a cantilever beam, and we can get a different mode shapes. Now, if my rotation speed becomes close to one of these natural frequency, a phenomenon will happen, which people refer to it as flutter. And what is flutter is something similar to resonance, but for continuous system, right? So flutter is the resonance for continuous system. So you saw with resonance, the resonance can lead to a nasty vibrations. Flutter the same. So your rotation speed coincides with one of the natural frequency, one of the modes, flutter will happen. In fact, you can do a simple test. Again, let me see if I can. Mass at the top. Not very, I show you with a slow motion, but it flutters like a wing of like a bird, it flutters. Anyway, so that's a phenomenon that will happen with the blade. And you can do the similar test on your own. So that's why when they do all the, let's say, design for blades, they need to take into account what is the maximum speed or the range of a speed that this one is rotating. So they design it in a way to avoid any of these natural frequencies, and luckily there is formula for the natural frequencies, right? This omega 1, 2, 3, and depends on how safe you want to be. And if still it's not piquing your interest, evolution also knows its vibrations and its cantilever beam. So have you ever wondered why all the, in cartoons, the mouse, they showed me like big glasses? So the reason is mice, they are farsighted, so they cannot really see. And they have eyes, but they cannot really see. That's again evolution because it wants them. So when they are in the dark, underneath, let's say in a hole, so they can navigate without relying on their eyes. And what they rely on is their whiskers. And these whiskers is the cantilever beam. So you can read this paper. It's very interesting. The end of this cantilever beam, at the end of this cantilever beam, it's a lot of nerve, which what it does, based on the excitation that it receives from the air, from the movement of other people, it can get to different mode shape. And I don't know how, but some scientists, they figured that and which is in this paper, but based on these mode shapes, they can realize if a person is, or an object is getting close to them, or moving away from them, or they are getting close to a wall, and many other things. So here about whiskers, they also like mice, they also like vibrational cantilever beams. All right. So any question from past topic? No, we're good. All right. So let's get to one more things before we get to the 2D wave motion, and that is, we want to know what is the vibration of the longitudinal vibration of a beam or a bar. So bar longitudinal vibrations. So let's say I have a bar. This bar, let's say, has length L, maybe density rho, and the cross section of this bar can be anything. It can be a rectangle, circle, a pipe, or any shape. You're not limited to the shape. So here are then the cross sections. And let's say the cross section has the area of A. Cross section, area. So obviously these things similar to a beam can have transverse vibration. What we discussed before was the transverse vibration or the lateral motion. Now we are interested in the longitudinal vibration, which also is important. So similar to what we did in the past, what we will do, let's say we set up coordinate, maybe we will go with X from the left side. At that coordinate, I'll separate a tiny element. Here, obviously, I exaggerate, but imagine this is a very, very small element with yeah. this is dx. So this element, let me draw it again. So this element, let's say somehow we excite this system, this element or this point can move left and right. You are in vibration left and right. So I set up my coordinate over here, and I call it U. So this U depends on X, where I am on this bar, and obviously time. So this is my coordinate. Again, this is just a general bar. Both ends are free, but then we can solve for a particular problem. So let's say this bar is under some load, some external excitation or motion, and internally there are some stresses and some forcing it. If there is nothing, then everything is zero and this thing does not vibrate, obviously. So let's say that the longitudinal load for these things on the left is P, on the right is something else. So I will write it as P plus the amount that this P is changed over this length dx, similar to the string and other things that we have. So I would say this is P plus dp, which again, I don't know what is dp, but maybe I can write it P plus the rate of change in P as a function of X multiplied by the amount it changed during this length dx. So here is my free body diagram. Then I need to rely on the Newton law. Sum of the force is equal to ma. So what do I have? Minus P plus x dx equal to the mass. So this element has a mass which I can write it as rho multiplied by the volume, a cross section multiplied by dx, and acceleration is derivative of u with respect to time. Right. Oops. Let's move routines. So E2 squared. Here is my equations. It's, as you can see, it's simpler than the string. For the string, we have to deal with the theta, but this one we don't have to. So I can get rid of P over here, dx, and dx over there. So I need to figure out the value for P, derivative of P with x. Again, we go back to the string and beam, always we try to get rid of the internal load, relate them to displacement or dcu or something else. So let's go rely on our mechanics of material knowledge. So we know P is equal to stress multiplied by the area, whatever internal stress that I have. And sigma, I can substitute it with based on Hooke's law by modulus of elasticity, epsilon E multiplied by A, right? That's Hooke's law. And epsilon, we know the definition, at the rate of change divided by the initial length. Remember, we are discussing about this tiny element, right? And this tiny element, its initial length is dx. And let's imagine that it changed by du. But again, since u is function of x and time, I use the partial derivatives, the derivative of u with respect to x. It gives me, epsilon E. I just use the definition of strain, right? Strain, if you recall from mechanics of material, the length, how much it changed to the initial length. So from here, I can take the derivative of P because C, I need derivative of P with X. Derivative of P with X, which gives me second derivative of U with X squared, AE. Combining equation 1, 2, and 3. I should have used my space. What is that? To make some room for myself. So let me bring all of these things down here. So if I combine all of these things, I will end up with, let's make sure that I don't make mistakes. So I have derivative of P with X, which is this guy. So it will be AE second derivative of U X squared equal to rho A second derivative of U. So I will end up with P divided by rho second derivative of U X equal to second derivative of U with T squared. All right. So I just get rid of A and I have E divided by rho. And like what we did in the past, we call this guy, because I'm second order, C squared. So I have then C2 derivative of U with X squared is equal to derivative of U T squared. And here is the equation for longitudinal vibration of a ball, which is exactly similar to vibration of a string, a wave equation. And you know how to solve it. Just as a review, let's quickly solve it. But I'm just going to give you a moment. So if you have any question to ask, or if you just want to take notes. And you should be able to solve this one. And again, always check to make sure your equation makes sense. If you look at like this equation, you have derivative of U X squared and derivative of U with time, which gives you acceleration. So you can see a trace of mass here, right? Rho, and a trace of stiffness here, which is E. So always that equation, mx double dot equal to kx, they are there, right? But it is just the stiffness or the mass, they have different form. Like for the beam, you saw it has E and I, and like for this one, it is like this. So let's solve this one. What we need to do is we guess an answer. So solution. So I go with Ux and T equal to maybe Ux, so this is small letter x, and cosine omega t. Okay. I'm trying to separate time and the displacement x. So if I go with that one, I need derivative of U x squared, which gives me double prime. I'm just going to be lazy, write it like that. Cosine omega t and derivative of u with time minus omega squared u cosine sine cosine omega t. Substitute there. So I'm going to get C2 all right. And derivative of u with time, it gives me plus omega squared u equal to 0. Because obviously we get rid of cosine omega t. And one more step. Prime omega divided by cu equal to 0. So I have one equation which is, they have to be all capital U, right? Make all of them capital U. So small letter u is the one that depends on x and time. Capital U depends only on x. U, that's U. We should use a different letter. So I end up with an equation which only depends on x, and it's a simple ODE. We know how to solve it. Again, we guess a solution. I go with ux equal to sine kx, so a sine kx. Substitute it there, I would get minus k squared. I have a square here, right? Plus c divided by 2 equal to 0. From here, k is omega c. So ux is a sine omega x c. Right? Anyway, you can check the calculation later if I missed something. So that's ux. So now I need some boundary conditions. Okay? So we need to solve it. So far is like general. For a particular example, let's say I have a bar which one end is being fixed. So I need two boundary conditions. One is over here, x equal to 0, u must be equal to 0, which is already, right? If you just look at the mode shapes, it does not give you any particular information. Or the mid those. So I need to rely on the other end. So on the other end, when x is equal to L, I don't have any information for UL, right? So similar to the beam problem, if you remember, for the beam problem, we rely on forces. So I know at this free end, so because it is free, P is 0. I don't have any force, it's just air. So if P is 0, if we go back and find P, we managed to find somewhere P was around here. It tells me that your derivative of u with x must be equal to 0. Do you agree? What I got from equation 2. If P is 0, derivative of u with x must be 0. So now I can rely on that one. Take the derivative of u. Oh, and again, this has to be capital U. Capital letter U. Solving for this guy, right? So derivative of that things gives me cosine derivative of u with again I'm writing is equal to 0, then cosine omega x divided by c equal to 0. If cosine is 0, it means omega x divided by c. Oh, sorry, you need to put L, right? At L. So omega L divided by c then is equal to, so if cosine of something is 0, it has to be pi over 2 plus, oh, let me write it. N pi plus pi over 2. 2n plus 1 divided by 2 pi. Anyway, it gives me omega is equal to 2 pi c divided by L 2n plus 1. And we know what is c, you can substitute it there and you're done. Pi n plus 1 L, and c is e divided by rho. So since I have n, I just put n, it means I have n natural frequency. Right, here are the natural frequency of a beam. Not a beam, a longitudinal vibration of a beam. And obviously the rest you can just substitute. So you have now u nx, which is sine omega nx divided by c, u xt corresponds is sum of all u nx cosine omega nt, and start from 0, go all the way to infinity. Exactly similar to the string. So if you understood that one, you should be having an easy time understanding this one. The only difference is this omega n has now a different form. Here we have e over rho, and here some different values. Sorry, what happened? Oh, A always, if you recall from the past, A always is there. Is that the contribution of the mode, which when we solve it for mode shape, we just put it equal to 1, like a unit, right? Remember we said these, the mode shape, they have a shape, but we don't care about their amplitude, we just care about their shape. All right, so please again review the equations for this one. Maybe try to, one good practice or one good example to solve is, let's say, what if you have a mass at one end? Then how would you solve? Which is like a very practical problem. Your TA said, Jacob, that some of you asked for an extra tutorial on continuous system. So, and yeah, I told him that that's okay, absolutely. So it's nice of him that offered this. And also it's a good news. It means that you guys are still into vibration. 12? 222. Oh, yeah, you're right. So this one is pi. This one is, thanks. One is omega n, right? Omega n is over there. And yes, it has 2 here, it has 2 here. Thanks. Please correct this time. You have a 2 here. So I suggest like these 3 examples, the string, the beam, and this one. Try to write down the equation for yourself. In your final exam, any of these, you are allowed to use the final form. Like, for example, for this one, for the string, you say, okay, this is the equation that we know. However, it's a good practice to know where it comes from, because then later, depends on the problem that you will get, you need boundary conditions. So you need to know what are the math that you get to that point. So with that, let's go to something more interesting, 2D. Vibration of 2D, okay, I want you to forget the 1D, the string, beam, and this bar, and get to the mood of 2D problem. We don't have 3D in vibration because if something is that thick, the vibration doesn't matter. We treat it as a 2D problem. So I'm going to go back 1 slide or 2 maybe here. Again, it's important for these topics to understand the concept rather than the math. The math, they are standard math, and you can figure them out. So here we had something which we call it nodal diameter, right? It was one point that it has 0 displacement for the mode shapes, right? And the mode shape, you saw there are some forms, like for a beam, it has some weird function of sine hyperbolic and sine and cosine hyperbolic, bunch of sine and cosine. So for 2D, the same. We have, maybe I can show you over. Okay, so let's say if I have a disk and this thin, and if I, no, I don't want to, if I calculate its mode shapes, the mode shapes, let me close this thing. You see those blue lines? Rather than just one point, now we have a line. So rather than nodal points, we have nodal lines. For example, this is one mode for a disk. It has a frequency for this disk, which is 1 millimeter. The diameter, outside diameter is 100 millimeters, I guess. And this is the first mode. So as you can see, those blue lines, they are not moving. All right. So let's go to second mode. Second mode, the frequency is 155 hertz, and it has now 3 nodal diameters, right? Or 3 nodal lines. We can call them nodal lines. And so on, we can go for higher modes. Now I have 1, 2, 3, 4, right? 4 nodal lines. So when a disk vibrates, again, combination of all these combine and make the total vibration of the disk. So similar to that, I can, now zoom is on the way. So for a complete disk, the same. So here is one mode, so 2 nodal diameters. And obviously I can show how they move. So the first mode, let's go to the first mode. First mode is like a mushroom shape, which is the dominant one. It's very, again, similar to, let's go to the string. The string would have like 1 shape. And I can go to the second mode. That's the second mode, one nodal line, or we can call it nodal diameters. This one is very similar to the previous one, but it is perpendicular to that. So this node, more like a Mexican hat, right? It is a nodal, it has a nodal circle. Okay, so no nodal diameters. In the middle, you can notice there is this one blue circle which doesn't move. All right. So here then we have something new. For 2D, we can have nodal lines. All right. Or if it's a circle, we can have nodal circles. So for this guy, the mode before that, it was one straight line, one diameter, zero motion. The second mode, which has frequency of something else, 500, something like that. And in the middle, there is a circle, which no motion for that. And similar concept, we go to the rectangular plate. So let's go to mode 1. It's very similar to the circle. So this is like the middle, goes up and down. And we go for higher modes. Very similar to circle, but this time our nodal diameter is along the diagonal. So if I go to the second mode, it's going to be very similar to this one, but perpendicular to that. And higher modes, now I have two nodal diameters, and so on. All right, so here is the concept of 2D. Why they are important? Well, imagine your car. All the panels for a car, they are thin plate, they are rectangular plate. You are on a road. If the natural frequency of a road coincides with one of the natural frequency of the car, then you will end up with like a flappy vibrations of the body of your car. For rotating system, like let's say floppy disk, grinder wheel, if one of these natural frequency coincides with the rotation speed, you know, the flutter can happen, which can be nasty. Let's look at this one. If I can play it.
So it's it's a great business to have. So you're looking at 30, 40,000 a month.
I got my commission.
Right, stop. Okay. Skip.
Or a Dyson, or whatever you call it, a vacuum cleaner. That's what it is. Yeah, American. Vacuum cleaner in American. So
The CD pieces will be
I reckon there'd be dust.
dust.
Dust. Yeah.
Dust.
There'd be no dust. Just a little bit of dust. Yeah, we've hooked it up. Got two washers here to secure the CD, and then bolted it in. Just going to spin it around.
So I'm excited because we're using a new Phantom today. This is the V2511, and it's the fastest camera we've ever used. At 720p, it'll do 28,500 frames a second, and at its lowest resolution, will do 1,000,000 frames a second.
So we've hooked up this Variac to the Dyson motor so that we can vary the speed and the power going into the motor, and then dial it up until it breaks and shatters, and see what RPM we get to.
Okay. Dan, I'm slightly scared.
I'm scared too. I don't know what's going to happen. Let me see how record time is. Okay, what we got?
2.6 seconds.
Okay, I'll let you know when it's about to go, and I think it's about to go.
Yeah.
Okay?
Alright, go for it. I'll run in there.
Okay, hang on, let me just turn this on.
I'll be like this.
Hold on. Okay, start it up. Not loads to go yet. Oh man, not yet. Soon. Ah! Ah! Ah!
Yeah. I thought it was going to go to the moon.
Yeah. It went higher than before. It went to like 100,000.
Did it really? So as you can see from this, 2,500 frames a second isn't nearly fast enough to see what happened there.
Let's look at what we got.
Right. You can see it warping. Look at that.
Whoa.
It's moving so much.
Oh my god.
Look at the shape of it. It's moving like the whole thing. Whoa! Oh god! Oh man!
You can look the whole video. I will post it there. And another one quickly. Let's just quickly watch that one. Imagine that you are one of these watermelons, but you are wearing the eyeglass.
Safety glasses.
Yes.
I think the shrapnel is going to crash the safety glasses through the watermelon. Yes, but we are going to now find out. This has unusable power. I'm going to put it full speed. Okay, now it's really dangerous and we have to go away.
Oh,
We all shop online, right? And when we do, we always see that little promo code field taunting us at checkout.
Okay, let's hope this is the flow.
so they have it in the disk.
Yes!
Have a nice. And here it is. All right, so just a second. If you missed the tutorial on Friday, I guess today is also repeat of the Friday. Your TA will send you an email for an extra tutorial if you decide to go with that extra tutorial. So we are almost done with the lectures. It's just a couple of extra formula for the disk, which the formula are not like the 2D wave equation will not be included for your study. In fact, like whatever we have up to this moment will be included in your exam. But Wednesday, as I said in the email, is our last lecture, which I'll do a quick review. I'll finish up the last 2 pages and then you're done. Thank you very much. How are you? Yeah, not bad. Let's go outside. The next teacher and next students when they come. What's up? No, no. Don't give anything bigger than 2 by 2. But you need to know, for example, for 2 by 2, how to impersonate. And what else?
You said it's focused on the later numbers.
Exactly. NDOF and continuous. But it doesn't mean that you know the previous. Because let's say even for 2 degrees, the setup, Lagrange equation, Newton law.
Okay, cool. It's 3 hours, right?
2.5 hours.
Oh, okay.
2.5 hours. Yeah, it's gonna be fun.
Oh, real fun.
Easy, I guess. But with the NDOF, I saw you. Okay.